Okay, so again, by doing the separation of variables, what we're trying to do is we're trying to solve the problem of what the wave functions are. So in the end, what is the probability distribution for the electron or for a particle that is in a central force potential, and in particular the probability distribution for an electron in the Coulomb potential, and so in an atom, and how that and what we're looking for today is just that how that probability density, how that probability distribution depends on the angular coordinates theta and phi. Okay, so we do the separation of variables. Okay, and then we plug that expression for y into our the Schrodinger equation, the part of the Schrodinger equation which is just the angular part, the angular equation, and then we divide by the product theta phi. That is, we divide by y. Okay, and this is what we end up with. Okay, so you can see that this left-hand side of the equation depends only on theta. Phi, theta, big theta is a function of theta. Here's a theta. Everything depends only on theta. L, if you remember, is what we're going to see is that that's actually an integer, but it's basically, this is L times L plus 1 is a constant that we got when we separated the r and theta parts, the radial and angular parts. Okay, and so this is a function of theta only, and this is a simple function of phi only. Okay, and so this, as usual, when we have two things which that are a function of two different variables, independent variables, and they're equal to each other, that means that they both have to be equal to a constant, to the same constant. Otherwise, it wouldn't be true for all values of theta and phi. Okay, and so both sides again are constant, and because you'll see why we use this notation later on, but both sides are equal to a constant, and we call that constant ml squared. Okay, m sub l squared. We'll see that that turns out to be an integer, but for the moment it doesn't matter. It's just a constant that we happen to give a funny name. Okay, so so now we can just rewrite these two equations where now we set them both equal to ml squared. Okay, and m sub l squared, and now let's solve the simplest one first. Let's solve the so-called azimuthal equation. We call it the azimuthal equation because, remember, phi is the azimuthal angle that's defined to be is sort of in the xy plane. Okay, so it's the angle that that sort of goes around the z-axis in our polar coordinate system. Okay, so this is the azimuthal equation here, and we see that this is now a very familiar form for a differential equation. We have the second derivative is equal to the function itself, and I should make sure to actually, this is big phi. Okay, so the second derivative of the function phi with respect to big phi, second derivative of the function big phi with respect to the variable phi is equal to some constant times the function right back, and we don't know at the moment whether ml squared is equal to positive or negative. Okay, but we can actually guess that it has to be equal to positive. That is, this quantity minus ml squared has to be negative, because that would give us oscillatory solutions, whereas if this quantity was positive, that is, if minus ml squared was positive, meaning that ml squared was negative, then that would give us exponentially decaying solutions. And the thing is that we have this wave function, the part of the wave function which is describing the motion, if you will, around the azimuthal direction. Okay, circulating around the z-axis. The boundary condition is that the wave function has to come back and meet itself smoothly, and that is impossible if you think about it with an exponentially decaying function. You have to have some periodic function.